Yeah. Good day, and thanks for joining this session. Let me start by a research study in 2014. A research study is done on learners of a foreign language, where two groups were studied, and as part of this research study, they identified 30% reduction in knowledge retention. So the study was done across two groups. The group A were the learners of a foreign language, which they were given a dictionary software, where the learners needed to key in or type in the letters that they are interested to look up for. And then we had group B of same learners of the foreign language, different group, but different dictionary software. And in this case, the dictionary software had an autocomplete and auto-suggestion feature, where as the learners were keying in 2 or 3 letters, the software were suggesting to them which one of these words you would like to pick. Now, you may guess, was it group A who had reduction in their knowledge retention, or was it group B? A or B? Group B, exactly. And these days, if you ask any software engineers, they're gonna tell you if you wanna learn software, if you wanna learn coding, you cannot learn by reading books or the tutorials. You need to get your hands on and start writing code. And that we all know that. We learn by doing, we learn by experimenting, by debugging, by fixing. Now, since advance of the AI is now, a generative AI specifically, is incapable of writing code for us, which is great, which helps us to automate a lot of tasks. But the question remains whether these AI-generated code or AI-generated code fixes, are they secure? Now, if we look at the literature today of the number of research studies, mostly in academic sector, on AI, whether or not AI can help us, you're gonna get a mixed result. I have included a few examples of this here. So in 2021, the study was done on GitHub's Copilot, and they have found out that 40% of the generated or suggested code from AI contains security vulnerabilities. A year following, another study was done, different groups of people, different models. They found out that LLM is reliable in fixing synthetically generated security vulnerabilities. In simple terms, that means security vulnerabilities with a known and clear pattern. This year, there was a research study that shows that LLMs are struggling to repair security vulnerabilities in enterprise or real-world software in 90% of cases without direction from a security expert. So as you can imagine, the result is a bit of mix. Now the question and the things I would like you to think about it, at the moment, we cannot fully rely on generative AI to write a secure code for us or to fix our software from security vulnerabilities. Now whether or not that day will come, I'm not gonna go to this argument whether AI would be able to. There are a group of people who are gonna say it will never fix our security bugs. There are people that believe in that. But one thing that both of these groups, they agree on that, definitely models need to become better. And the question remains, who will generate or who will build these models? So as we all know, these models are built based on the available data. In fact, a lot of security suggested code from AI model these days comes from top answers from Stack Overflow, which, by the way, being a security expert myself, lots of them does have security issues, and hence AI also suggested that. But anyhow, if we want to reach to that utopia that AI gonna fix also security vulnerabilities, we need a group of experts. And please don't look at the security guys like myself gonna do that. It's actually the job of more on software engineers and people like yourself who writing code and building software. But we are at a very interesting time in, I think, the history of the programming where AI started to generate a lot of code. And if this generated code contains security vulnerabilities, the new models probably gonna get trained on those generated code as well. For me specifically, I was interested to know whether any of these AI-suggested code help our developers today to become better in secure coding. It was a simple question that I just wanted to find data to prove whether or not a generated code or generated suggested code from AI will be helpful. Before I start my experiment, just quickly on myself, my name is Pedram Hayati. I live in Sydney, Australia. I'm CEO and founder of SecTeam. We have built a fun and engaging war game to skill up developers in security. I have been in the security scene back where it was not even called cybersecurity. And I also teach at University of New South Wales, as you guess, in the cybersecurity field. I happened to did my PhD in machine learning when that was not even a hype. We were dreaming one day the machine can, by 50% chance, does better decision than human. Obviously, that has changed. Coming back to the experiment, we do run a large number of public and private secure coding contests for conferences and for companies. So we do receive lots of different submissions for different security vulnerabilities. And as part of one of the most recent security the conferences that we hosted, one of our secure coding contests, we looked at the submissions for one of these contests that we executed. Just to briefly tell you how the experiment whole setup worked. We have given that audience, there was more than around, I think, 150 of them, examples of secure coding challenges across different coding stacks, across different languages. Each of them contain a different types of security vulnerability. And the goal was for anyone to go and find the security vulnerability, use the whole familiar GitOps operation, push the code, and they will get a score. There was a leaderboard, so the players who have submitted the code earlier or they solved most secure coding challenges, they will be the winner. Now, the way that the whole experiment set up is that it's pretty easy. So this is just an example of it I'm showing here. There is a leaderboard. You can look at your ranking among the other players, and there are different secure coding challenges you can pick from. But one thing we have noticed, since we provide devs with the full code repository for an application which has an intentional vulnerability, they are also able to clone this whole thing locally and using their own IDE, their own agentic AI. And since, I would say, a year and a half ago, we start seeing people are using AI, and these days agentic AI, to solve these secure coding challenges. So this will allow us to be able to effectively do this experiment because we can see who actually used AI or not. So coming back to the presentation, for this experiment specifically, we looked at 420 submissions that developers have done as part of that contest that we have executed. And out of these 420 submissions, we looked at these metadata. Whether or not that submission resulted into passing that secure coding challenge, number of commits, the nature of code changes, whether there was adding something to the code, deleting something, or replacing some lines of the code. And we looked at minimum, maximum, and average amount of code diffs, time diffs, and file changes. The result was rather interesting. The first thing that was quite obvious, which I will go through as part of this presentation, was that there was a clear behavioral pattern distinction between AI-suggested code fixes to the human-written code fixes. For example, if we look at code diffs, or the differences in the code, as you can see in the graph, what you can see on the AI side of the thing, you can see the AI-generated code was 3 to 4 times larger than human-written code. In fact, AI-generated code mostly were example of text-based suggestions that you probably find online about how someone should go after addressing a security vulnerability, or better than that, hardening their apps and adding multiple layer of security protection against something. The other thing that probably if you have used it, you've seen it a lot, is AI is pretty good in writing comments and does a lot of error handling, and that we also see in this submission. Comparatively, the human written code, you could see that the code changes typically are targeted toward the vulnerability itself. So there is no other wasting time around, or let me just add this best practice coding here, or changing the variable names, or adding the comment here and there. Was mostly going after that line of the code or block of the code which contained the vulnerability. I will show you an example later on, and fixing that. Another interesting factor was time. AI-generated code fixes was at least 3 times faster than human written code. So what I mean by that? This means that someone cloned the code locally, they used their agentic AI, and with whatever prompt that they were interested, they asked it, hey, can you fix the vulnerability in this code for me? And they just did simply git push, so those changes were pushed to our upstream server. Anytime we received any new commit from any players in this secure coding contest, we effectively attack the code. We run a number of tests against that code to ensure if the security vulnerability is passed. So this is a time, or the amount of times that how quickly they push every single commit. So as you can see, the bar in purple color, majority of the AI submission was done in less than 10 minutes. Versus if you look at the blue or grayish color, I'm a bit colorblind now, with regarding to human written code, you have a uniform timing across, anything from 2 minutes all the way to more than 1 hour. For someone to get the code, try to reason about where the vulnerability could be, and then push. Now, these two heuristics are pretty interesting. You will see toward the end why these two could be quite useful for us today to monitor how our team is operating. But it didn't really answer the question that we had in mind, and whether or not these AI-generated fixes help our software engineers to learn or become better in secure coding. And for that, we needed to dig more deep in more examples to really understand, to kind of extract more data from these submissions. So what we have done here was we looked at the table on the top right. We looked at 3 metrics. Maximum commit size, so this is the size of the commit, the amount of changes that they do in one commit. Commit per repo, the number of commits that they pushed to any repo. As I mentioned, every secure coding contest was a repo. And the number of lines that has changed per commit. So we looked at all these numbers across both AI fixes and human written code and averaged it out. Now, if you look at the ratio column there, it's pretty obvious that there is a huge difference between AI fixes versus human written code. For example, the maximum commit size for AI fixes are almost 9 times larger than human written code. Or in the case of line per commit, AI writes 5 times more changes, or introduces 5 times more changes to the code comparing to the human written code for exactly same vulnerability and same app. Now, the other interesting part was the table you can see on the bottom left is we look at 3 developers who have used AI to solve one of the secure coding challenges, which I will show you in a moment. This challenge difficulty was something between easy to medium, and I will explain how we usually measure the complexity of these secure coding challenges. But what we looked at in these 3 repositories, or these 3 submissions, were firstly the number of lines that has changed, But the other thing that we have looked at is the time, because in the Git commit you get time, so it's the best way for us to measure, given that many line changes, how many times it has taken. Now, if you look at the first one, the first row, you can see almost 500 lines has been pushed in less than, or this is around 50 seconds. So we are talking about the speed of typing or writing 591 lines per minute. Let me simplify that for you. That means you are able to write 10 lines of code per second. So if I borrow even my toes and maybe a couple of more hands, I don't think I will be able to write that many lines of code per second. Now, we're not talking about comprehension and reading. So that is completely unimaginable, and we know it because they use agentic AI. But this is where the interesting part comes in. There are a number of research done in terms of how we as a Homo sapiens, we can learn. Or if I've been given a technical book, on average, how many lines I can read per minute and comprehend. And the number is between 50 to 100 lines per minute. So even if I'm a superhuman, I probably can read 100 lines per minute and understand what has been written. This is just reading. So if you compare these two numbers, 10 lines of code per second written, and as a human being, I can only comprehend 100 lines per minute just reading it, it is physically impossible for anyone to not just write this many code, let alone comprehend what AI actually suggested, let alone tweaking it to make sure this has really fixed the security vulnerability. So in other sense, put it simply, they just accept them all and just Git push it up without even thinking about whether or not, or just let's just look at, let's just see what AI is suggesting here. So probably I can learn something from it. Maybe it has found a security vulnerability, or maybe it has just missed something. So they were all examples of where they didn't really care. They just got whatever output came out of the agentic AI and then pushed it up. Let's look at the examples for a few moments. So what I'm going to do now, I'm going to look at, we're going to do a code review together for one of these secure coding challenge, which is one of my favorite coding challenges. We are going to first look at, I'm going to first show what the vulnerability is. Then we're going to look at how a developer, we're going to look at the human written patch for it, and then we're going to look at the AI equivalent of it. So first of all, the vulnerability I have here is integer overflow. How many of you have heard about integer overflow? Oh, this is amazing to hear, because it's interesting. This security vulnerability is probably older than my dad, but is still around in 2025. And I'm not talking about C or C++ code and assembly code. We do have this vulnerability happening today in Python, in Ruby, in C#, in Java, especially today if you are using any AI SDK or machine learning SDK, because they do use some native data types, you're going to have this vulnerability behind the scene. And this was example of that. We had example of integer overflow in a NumPy package, which is the most popular package used in Python for dealing with numbers, especially large array. So this is an example of one of those applications that we have been given to the developers. Now I'm just opening for you the file that contains that vulnerability. Is really simple. Now, what this code doing effectively, it takes one number, untrusted data from the user, an input. It does a simple arithmetic on it, and it makes a decision. So if you look at, first of all, we are importing NumPy, because as you know, for performance, speed reason, you don't want to use the Python's default number type. You want to use something like NumPy, which is behind the scene. Use C implementation, which is a lot faster. So here what we have a value called threshold, and this value is calculation of this number. Just think about it. This number here is threshold. Now over here, we have a simple function that takes a value called days, and what it does, it multiply days, whatever comes in, with effectively it takes seconds out of it. So it just calculates how many seconds existed in that many days. And then it just compares if this value, the result of these days, is bigger than that threshold. If so, return true, otherwise return false. This was an example of an easy to medium complexity challenge because to guide the developer how they may go after fixing the vulnerability, each app comes with two sets of test suites. So the first one is usability test. This is like effectively checking for the functionality. It's effectively giving the app some numbers. Like for example, in this case, it provides the app with 100, and it calculates whether the app returned 200, and it printed that system is optimal, and so forth. So we can even go ahead and run these tests, and as we can see, by default, all these passes. But the interesting parts, those edge cases that usually as a software engineer we miss are these edge cases. Now, if we give this app specific numbers, such as 249 or 1,337, or even 0 or -1, this is a time that we are hitting some of those edge cases that will result into integer overflow. We can run it, and you can see, by default, these security tests are failing. So all the things the developer needed to do was effectively following these security test cases, going back to this file, and just write enough code to passes those, and that means they have passed or they have patched the security vulnerability. If you are interested to see how these things is, I can run the app just to show how this thing actually works. So the example of app is this thing that we see here. It's effectively simulating Boeing 787 power generator system. The reason is, sadly, this security or this vulnerability existed in the Boeing 787 power generated system, the onboard system. And after 248 days, the system was shutting itself down. I'm not joking, this was actually a bug within there. And they did investigation on the Boeing, and then they figured out this is due to the integer overflow vulnerability. So this is effectively what we are simulating here. So what I have here is an auto increment that increases the number of days, and I can even increase the days here. So maybe I go to this Boeing is operational within, I don't know. Let's just go 7 days. Up until 7 days, seems like system is optimal, so things are working fine. If I go, for example, to let's just say 200 days here, I check the status. Still system is optimal. Now, if we are hitting 240, just say 5, I start the auto increment. This is where the system, after passing a few more days, it's gonna start, just 245, check the status. Yeah, we are getting to a bit dangerous area, and then once it passes 247, this is where the integer overflow happens. And this is where the system was actually starting to shut itself down. Danger. So why this thing happened, if you guys are curious, is all because behind the scene, regardless of whether we are using a type-safe language or untyped language, behind the scene, things need to allocate parts of the memory. And a compiler or interpreter need to know how much in the memory they need to allocate the space. Now, when we are dealing with a number, the system by default will pick a certain size within the memory and will say, okay, this number that I'm gonna do arithmetic on, it's probably gonna be between this range. The problem happen is that any arithmetic, and by arithmetic I mean you add something, you multiply something, that value goes beyond that range. I'm not going too much in detail now, but what will happen, and we can blame the CPU manufacturer, by the time we reach to the highest range or the lowest range of that number, the number wraps around. So if you have a positive number, suddenly that's going to turn into negative. If you have a negative number, that's going to suddenly become positive, which is horrible because imagine you have a banking application, a back-end application that takes numbers from users, just their account I don't know, their balance in their account, and they try to pay someone a specific number, a specific amount. Imagine if you enter a pretty large number that goes beyond the range of that value in the memory system of that backend application. And trust me on that, there were banking applications that they end up refunding someone rather than paying because the number wrapped around and become negative. Negative in a lot of financial systems does mean refund. So if you are writing code, just if there's first thing you want to take out of this code, if you're dealing with number, please do remember behind the scene, this thing's gonna allocate a fixed space. So just ensure whatever number you are dealing with is within the safe range. And that would be a simple check that you can do in your code. Anyway, it was a little bit of sidetrack, but I come back within the code. So how do we fix this? Now, the fix for Python is rather simple because, first of all, let me mention a few pitfalls anytime when we go patching or addressing integer overflow. A lot of times we have seen the way that people try to patch integer overflow is that they try to change integer to long, or they try to change integer 32-bit to 64-bit. That is not a solution. Why? Because, okay, now I don't have integer overflow, I'm gonna end up having long overflow. It's just a bigger number. It doesn't address the problem. And sadly, this was one of the recommended answers in one of the Stack Overflow questions, and you will find it a lot of time that is being suggested as a solution to integer overflow. And I think the other thing is the name of integer overflow is a bit misleading because we think that it only happened to the integer, versus the better name that we usually refer to it is more numeric overflow. It can happen to any number type, regardless they are integer, they are float, they are long, they are double, integer overflow can happen. So a safest way for us to address this is not upcasting, is by using what is known as a dynamic data type. Dynamic data types, if you guys are Java developers, big integer is an example of a dynamic data type. We also have it in C#. Now in languages like Python and Ruby, because theoretically they are on type, anytime you move out from packages such as NumPy to use the default number type, behind the scene, the interpreter does use a dynamic data type. What is the benefit of dynamic data type? The main benefit is that effectively you do not have a range limit. Theoretically, your limit is the memory limit, or the allocated memory limit for that program. So that means a huge number. The way that Python interpreter and Ruby interpreter works is that by the time the number goes beyond the range, it allocates a bigger size to that number. So you don't really get the integer overflow problem unless someone goes really massively long. Probably they're gonna hit some other problems before integer overflow. So what I have done here, a simple change from threshold that is defined by using NumPy. I just comment that line out, and I'm just simply calculating threshold by doing this. The other change I have done, rather than I use NumPy to do multiplying these many numbers, I comment at these lines, and I just go back and use a simple arithmetic. So I just add days, multiply that 86,400, multiply to 1,000 just to get centisecond out of days. So that is there. If I now run, first I will run the usability test, so I have not broken the app. I run the security test. Probably this is still failing because of the error handling that I need to know. I go back to the view, and I just prepared this before this talk. So what I'm gonna do is I'm just gonna comment this line out, put this in a try catch, and if this value was anything other than integer, I will be handling that. And if the value is less than 0, I'm gonna just say this is invalid input. That's all I'm doing. Let's just run the security test again. Still I have a problem. Let's just look at where I have, I don't have result, probably here. Bring it down here because I want to make sure I do the result after I do some checks. So what I'm doing, I'm doing some effectively input validation right before sending this untrusted value days back to this function is optimal. So there's some validation here. One of the things I would never send is I shouldn't send any days less than 0. This is theoretically doesn't make any sense. And that should be it. Oh, yeah, I also need to save this file. Let's run it again. And hopefully, no, let's just see the integer literal one. Yeah, so this one here, probably, let's just try that. Hopefully this will fix it. Yeah, so I pass it. And if I run the app again this time, and hopefully it's not gonna show me any danger or situation like that. 245, check the status, let it run. Let's just see if it's gonna overflow after 240, yeah, 47, 49, yeah, still doing something. But what we are seeing, it says reboot is required. So it kind of, it is a behavior that we are expecting. It doesn't go back to the system optimal. Okay, so that was all about the code. Now let's just go back to the slide, look at, well, how our developers actually fixed this. So this is a submission from one of the developers who passed the challenge. So as you can see, they only did a single commit, and the commit contained 2 file changes. Majority of that was adding something, so 10 insertion and 4 deletion. And that was it, and they passed this challenge. Looking at the diff, as you can see, they actually followed the same structure that we just did. They just moved from a fixed data type to a dynamic data type. Same but here, the arithmetic is done here, and a bit of error handling. Done. 10 lines of code changes, or effectively less than that, and you're fine. Now let's look at some of the AI suggested fixes here. So what you see here is 6 commits, and the frequency of them are pretty interesting. Like some of them come every few seconds after each other. But more interesting is the number of code changes. So in the first commit, we are seeing around 31 insertion. But in the commit following, you will find 21 deletion. So it's effectively like, okay, let's just push this code. Oh, it doesn't work. Change the prompt, push something else, and the next commit will kind of remove whatever change that was done in the past. And it's kind of a pattern of frustration. Like you push, and it changes some of the files which was completely unrelated to the security vulnerability. And there is a reason for it. Like one of the changes you see here, it moved the debug equals to true, the debug equals to false. Okay, it's a best practice that you don't want to enable debug in a production. Is a good one. Or the other change, limiting the allowed host that can communicate with this app to only the local IP. Again, a good thing to do, but again, this is not the vulnerability. The most interesting part is this part here. Anybody heard about HTTP security headers? Something good to do, right? If you're writing a web application, probably you want to include some of those HTTP security response header. Things like XSS protection, content type option, a textbook's example of security suggestions. But this is not going to address integer overflow. It's good to have. It's very well written. I mean, it's very convincing to me. Well, it's doing something, but it's not going to. And then the next commit is like all about formatting, reformatting something, changing the route, which I have no idea what is going on. And then the commit after that, deleting it, changing, I don't know, the allowed house to environment variable. You can clearly see that, or changing the secret key here. A lot of things done, but unfortunately, none of them was really toward fixing the vulnerability itself. All in all, what at the moment we are seeing is that if we use these AI-generated code, specifically when we are learning about secure coding or coding in general, there's a clear adverse impact on our ability to learn. Because one of the things that you will see is over-reliance. And once we consume the data, we give away the driver's seat. We become more like a passive consumer of this information. And this sadly has a significant impact in our critical thinking and problem solving, which are the two key things, especially when it comes to the security vulnerability, because you really want to get down to the root cause of the problem and addressing it. The other thing is, as you could see, that some of the suggested code are really professional looking, and we're gonna get into this optimism bias that, yep, this looks professional, so probably this is gonna address the problem. But in reality, that is not the case. Now, although our experiment was small in size, the interesting part is pretty much aligned with all the other things we find in the literature, not just specifically in secure code learning, but also in code learning in general. That they will find that as learners, they will start using AI in a wrong way, their ability in knowledge retention, their ability to think critically about the problem diminish over time. Some recommendation going forward. Obviously, I don't want to say, oh, let's just stop using AI. That's definitely not the case. But there are some things that probably at the moment we can do to be better in using generative AI. First and foremost, if you are a learner, there's one most important thing we can do is please allocate time to review, to critically scrutinize that generated code. Because that is probably the only way that you can also help yourself in learning and at the same time understanding what is going on and keeping that driver's seat. One other suggestion I have is that you can, these days, in your IDE, you can switch your LLM model to something else. After generating code and you're testing it and it works fine, probably switch that model to something else and get the different model to review your code and try to understand the output. Often that will help, again, to understand these codes. So please never accept code changes that you do not fully understand. This is just for you. Now, if you're a code reviewer or a team lead, I think one of the most important checks today we should put in our build pipe is the check for unaudited AI-generated code. And some of those heuristics that early on I mentioned in the talk, things like if you see there is 500 lines of code changes in 50 seconds, that is a strongly indication of an unaudited generated code that probably you do not want that to get in any of your production branches. So that would something I will definitely flag or probably stop the build, because that's a code that shows there's someone has not done review of that code. And obviously reminding your team on the risk and potential downside of the AI reliance. Lastly, I would like to leave you with a few resources for learning. So there are a large number of secure coding community challenges that you can use. On SecTeam, you can go to that URL. There is a project, OWASP Juice Shop. It's an interesting project because there is an example of different vulnerabilities that you can play with. It doesn't have that much of the secure coding. It's mostly about exploitation and finding these edge cases that result into a security vulnerability, but that will actually help you to understand the edge case that result into the issue. There is a secure code learning GPT that you can search in ChatGPT and you can get some idea on that. And if you are an MCP server user, you can use our MCP. It's trusted. We are not using any dodgy code. I don't know whether you've been in some of the previous talk about MCP, but those are also useful. Okay. So that was all I wanted to talk about. There is a blog post attached to this talk. If you are interested, you can read more about, and all those research literature topics that I mentioned, they are also referenced there. Thanks so much for your attention, and if you have any question, happy to go through them. Yeah. Codex, no. No, we didn't know. We didn't know what model they use because we just get the the result from them. Yeah. Any other question? Yep. Commit or originally when how we marked it? Yeah, well, good question. The first thing we did was originally was looking at the nature of code changes, especially when it was a textbook's example of like fixing something and when it was a lot of comments involved, a lot of unrelated error handling. You know, when you are when you're doing a secure coding contest, you don't have time to write a clean comment about why I'm introducing this function, right? So those are the things we started with, but then when we saw the results such as time and code diffs, these were also used to further enhance it. Okay? No other question? Thanks for your time.